to the SEPM Deep Water Research Group 2025 online virtual forum. We would like to welcome you this morning and thank you for joining us. And we would like to start out with a few announcements and welcome you before we get started.
Absolutely. All right. Thank you, Cassie. Well, hello, everyone. Thanks for taking the time to log in. I'm Fabian Legier. I'm going to be speaking a little, kind of emceeing this whole thing, but this has been a lot of work to put together, driven mainly by Lillian Navarro and Emma Morris, as well as Stan Stanbrook. All four of us are on the Deepwater Research Group Committee. And thanks again to Cassie for all the work that you've done in the background to put this together. So we're here for the SEPM Deepwater Research Group Virtual Forum on contourite systems, processes, products, and applications. But before we get in and get into the great speakers that we have lined up, just a couple comments. Let's see if this actually moves. There we go. Kind of the theme or the approach we want to have within this forum, right? We want to reference the SEPM's code of conduct. We really want to encourage throughout this whole session and all the other activities and events going on throughout the year, that SEPM encourages open, very respectful dialogue across all those activities, including this virtual forum. Right? SEPM is committed to a very harassment-free, intimidation, discrimination-free experience for all. And bringing that concept in, right? We want to respect the diverse views. We want to critique ideas, not individuals, and have a discussion around that. The expectation of everyone involved here is that we show respect, we collaborate, we have open communication, and we reject harassment, disruption, and unauthorized recording as well. So by participating in this, everyone's agreeing to abide by these codes of conduct, and by doing so, we'll have a much more involved and beneficial forum, I think. So going on into what we're going to be looking at today, we have a great group of speakers lined up, and it's great to see so many colleagues joining from around the world. We've got researchers, we've got students, we've got professionals, all who have signed in. And the goal here is to drive an increase in the understanding of the deep marine record, right? And so today we're kind of continuing SEPM's mission to create that collaborative space where we can have innovative science, open discussion, and drive that understanding forward. So this year, the focus is on the complexity of the diverse processes that shape deep water depositional systems, and we're particularly be emphasizing benthic currents and contour currents and the resulting contourite deposits. So we have a really good line of speakers today, and across their expertise, we're going to get to explore what I would kind of place into three broad themes, right? We're going to focus on currents, contour currents, right? Advancing the understanding of those benthic current dominated systems. We're going to look at this across a variety of scales, from seismic scale models to conceptual paradigms, and refine our understanding of those processes. We will be discussing processes and mechanisms, so investigating the physical drivers of that sediment transport and accumulation, looking at internal waves, looking at the mobility of mud aggregates in deep sea settings. And then we're really also going to be trying to bring this together and discuss integration and application. So connecting those observations across all of those scales and methods, from outcrop to subsurface, to modern observations, kind of bringing that process-based understanding into our stratigraphic understanding. And together, we're hoping what this shows is how the deepwater research community, that's continually evolving, right? As new observations are made, as new techniques are developed to analyze data or to develop numerical or experiments, we can bring more and we can kind of push our understanding of these systems more forward. The goal of why we're having this forum the way we're having it, right? The aim is we want to integrate ideas, right? We want to connect those scales. We want to encourage dialogue across a diverse range of perspectives on contour currents and contourite deposits, and we want to advance that understanding. So as we begin, let's remember that this is a collaborative science. All the studies we're showing here and all the work that's going on in the background, we encourage discussion on that. So we thank all of you for taking the time to join us and for your curiosity on this. And please enjoy the forum. The way we're going to approach this is after each talk, we're going to have a few minutes for questions. Feel free to type your questions in to the chat, or feel free to just raise your hand and ask that. After the third talk, so after Kevin, we're going to be having a small break, and then we'll go back to another round of 3 talks with some questions after it. So thanks for joining, and yeah, let's begin. Our first speaker today is going to be Dr. Elda Miramontes Garcia. Please take it away.
Okay, hello everyone. Can you see well my screen?
Yes.
Yes, okay. Well, thank you very much for the introduction and for the presentation. So today I'm gonna show some type of contourites and the processes that form them that might be a bit more different to what most of us have in mind when we usually talk about contourites. Because, well, contourites are typically defined as currents formed by the deposits formed by the currents that flow along slope and form these large contourite drifts that we find along many continental margins. But actually, in the official definition nowadays, we consider any kind of bottom current affecting the seafloor can also generate contourites. So in the ocean, we have many different processes. Of course, we have the along slope currents related. Yeah, so they are mainly related to the thermohaline circulation. But we also have many other processes that affect at the shorter time scale. So we can have variations of currents daily related to internal waves, for example. And they also tend to affect smaller areas on the seafloor. So the question that we pose to ourselves as sedimentologists is actually, well, from all these processes that we can find in the ocean, what is really controlling sedimentation, seafloor geomorphology, and what is affecting the currents in different time scales that will be what is actually going to be recorded in the sedimentary record. So when we talk about a contour depositional system, we can have many different structures at different scales. So first, at the large scale, so several kilometers scale, we can find, for example, plaster drifts and related contourite terraces, and they tend to be formed by long-term processes related to the thermohaline circulation. But if we look at it more in detail at higher resolution at these structures, we start seeing some small channels, some ripples, some bed forms, and then we start having more and more information from this kind of deposits because, well, technology gets better and we manage to image in different environments already more resolution the seafloor. And these deposits are typically formed by internal waves and other high frequency processes. So internal waves are very often related to tides. So when we have the transformation of the barotropic tide interacting with the topography, then this can generate some baroclinic tides that will propagate in different ways in the ocean. So for example, when we have the formation and the critical slopes of rays of internal tides that will then propagate across along the ocean, they can also form nonlinear internal waves that will propagate around pycnoclines, and you can even see them very often on satellite images when they are propagating near the sea surface. We can also have them when, as a leeway formation, when there is an interaction with an obstacle. That's very typical in straits, for example. And then when we have the ebb and flood currents, this can generate on the top of the seal some internal solitary waves that will propagate and at some point will break on a slope. And we see in many environments this interaction of internal waves with the seafloor. Here's an example from Northwest Ireland in the Rockall Trough. You see here with a sub-bottom profiler, we have a contourite terrace and a small drift, so a terrace drift system. So the whole slope has several of these terrace drift systems, and we could see how an internal wave was breaking exactly on the top of the terrace. So we think that this interaction is also remobilizing sediment from the sea floor and helping the formation of these terraces. We also had at the same time a CTD profile with turbidity measurements in the same location. And you can see also how in the area where we see these higher amplitudes in the water column, we have more particles in suspension. So we have the generation of nepheloid layers, so zones of water in the water column with high amount of particles in suspension that remove sediment from the slope and take it further to the open ocean. And these waves are actually really big. In this case, over 100 meters of amplitude, so it's much larger than this the Liberty statue. And if we compare it with the largest waves that we can find on shore, so it's the very famous Nazare wave, where these giant waves are served by some very courageous people over there, but they reach only up to 26 meters. So here we are talking about even almost 4 times larger waves that are gonna break in the seafloor and create very strong currents also at the seabed. And so there was a study that simulated this interaction. And here you can see how internal wave propagating in the pycnocline breaks on the slope, and in color is the sediment density in suspension. So you see a current that moves upslope, that some boluses that keep propagating upslope, and then the material gets trapped within the pycnocline, and we have the formation of a nepheloid layer. So you can imagine that the same time that all this material is being resuspended, we are going to have also the formation of some particular structures at the seabed. And this has been observed in many different measurements of the water column. Here, echo sound image simulates, shows a very similar feature as was simulated in this study. Also, we had recently a cruise offshore Mauritania, and we observed again very similar features in the upper slope and shelf edge. So here, what you see, this is the water column. We have a nepheloid layer that starts at around 300 meters, 300 to 500 meters with the depth, and then it propagates offshore. And in the zone of the generation of the nepheloid layer, we have a field of bedforms. So we have first scours, so we have erosional features in the deeper part, and then in the upper part, we start having a field of bedforms. And here in the sub-bottom profile, you can see how these bedforms that are quite large, several hundreds of meters in wavelength, they migrate upslope. And interestingly, also below this zone of generation of nepheloid layers and these bedforms, we have a chain of, or 2 chains of coral mounts. And actually, it's a very typical combination that we tend to find bedforms and erosional features in zones where we also find coral mounts, because cold water corals, they need particles in suspension, so here they get everything they need from the interaction with the internal waves. So at the end, this interaction between internal waves at this seafloor generates nepheloid layers, so we have a lot of material in suspension, also creates some particular bedforms, some sediment waves migrating upslope generally, but sometimes we can also find erosional features. These kind of bedforms have been found in many different environments. For example, also in the Messina Strait. Here we have the generation of internal solitary waves at the seal, and you see them propagating northwards here. And in the zone right at the seabed, in this area, there is a field of sediment waves, dunes in this case. They are made of sand, and they are also moving in this direction. So it has been suggested that they are formed by the interaction with internal solitary waves. Similar also in the South China Sea, there are some huge fields of sediment waves and erosional channels, and it has been suggested that they are related to either internal solitary waves that are breaking on the slope and interacting with the slope, and also internal tides that are creating currents up and down in the area, and probably the diversity of erosional features, orientation of the bed forms, and also direction of migration of the bed forms depends on how these waves are going to interact with the seafloor. And this depends on the type of wave, but also on the seafloor slope and seafloor morphology. In the Mozambique Channel, we have more examples. Here there is in the upper slope a field of dunes. They are made of sand. You see also here covered by ripples, and they migrate upslope, and they decrease in size also upslope. And before the dunes start, so further downslope, we have an erosional surface. So all of this rather indicates that we have a current going upslope related to this interaction with internal waves that is generating these bed forms. But you can see here in the topography that actually there is a main crest, but we also have some other orientations, the secondary ones a bit smaller. So probably it's not always going also upslope, but we might have some reflection in a different direction that can generate some secondary dunes. In the same area, but of the margin, but a bit farther south, instead of having a field of dunes, there is a huge channel. And this channel is located in the upper slope. You can see here it extends over several kilometers. It's relatively small, but this is there. And the interesting thing is that actually we have a similar one preserved in the sedimentary record. We can identify it here very well in seismic. And we know that it was formed during the last interglacier, because in the area, this area is in front of the Zambezi Delta. So during the low time, we have a very high sediment supply, and the currents, even if we have internal waves and the currents are still strong, if we have too much sediment supply, they are not going to be able to erode so efficiently the seafloor. So we tend to have these erosional surfaces during the periods of relatively low sediment supply. And the idea that we have why we might have such a continuous and straight channel, there is no obstacle, it's just in the middle of the slope. You see here it's just continuous and suddenly a channel. So the idea is that probably we have an internal wave coming, but in the area we also have barotropic currents, barotropic tides that are gonna be affecting the area regularly in a different direction. And we speculate that probably what happens is that when the internal wave is approaching, and we have also the tide, the barotropic tide coming from the shelf going in the opposite direction, it might stop the wave for a while in the area, and that could make that it's always breaking and affecting the slope for a longer time in the same place, generating focused erosion and not just a broad erosion on the seafloor. In Namibia, we also observed the interaction of internal waves with the seafloor. Here is again a zone with abundant coral moss. So you see here now we are in the shelf, mid to outer shelf. And here you see in the lower part a lot of erosional surfaces and several mounds that are formed by cold water coral mounds. And here is a huge escarpment and channel that extends along several kilometers and is again very straight. And in the zone of the channels, of the mounds, you see also some channels that are oriented across the slope. So these mounds, the coral mounds and the channels, were modes and drifts. So you see here some modes along the ridges of the coral mounds and some drifts in between. They are oriented across the slope. So actually these features are not formed by a long slope currents, but rather by internal tides that move across the slope every day. So in addition to that, there are internal solitary waves that we can even see from satellite images approaching towards the shelf. And we could image with our parasound data how they propagate in the water column. So you see them. These are the same time as the cruise, both images. So you can see these internal waves approaching, and then we can see how they break here at the escarpment, where we have this very big erosion. And concerning sedimentation, actually the area where we see this strong interaction of internal waves and the seafloor, we have coarser material and also less organic matter. And we find in between, so in the areas that are a bit calmer without such a strong interaction, we have mud depositors and more accumulation of organic matter. We have also some seismic in the area. So we can prove that these channels and this escarpment and erosional surfaces are not related to any tectonic structure. You can see all the units below them are completely continuous and no tectonics going on. So we know that it's all related to sedimentary processes. There are no submarine channels either in the area, no turbidites that can be found. So we think that the role of internal waves in this case must be very strong. The sediments, we have also some analysis of surface sediments in all the area is mainly muddy sand to sandy mud, and it looks a little bit like that with still quite a lot of some fine grained material in there because it's a zone with very high productivity in the surface, so we still have some accumulation, but this is what generates at the end, gets resuspended by the interaction with internal waves and will generate the nepheloid layers. So we have also some turbidity measurements of the water column, and we can see that in this zone here below the escarpment, where we have the coral mounds and these across the slope modes and channels, is where we see also in the water column some nepheloid layers coming out of this region. And you see again in this case the internal waves approaching the escarpment and then breaking here, making like a hydraulic jump, and probably this is also enhancing over time the erosion in this area and making this escarpment and channel larger and larger over time. We also have some measurements from a short-term lander that was situated on the top of the escarpment, and we could see. We also have some turbidity measurements, and we could see some changes in the turbidity. And these changes, these peaks, very fast changes in turbidity, they were always linked to strong changes in the direction of the current. And interestingly, it's not necessarily the moment when the current is the fastest. So what we interpret from here is that probably this is also related to the interaction with the internal waves, because we are going to have different processes moving, and as we saw in the simulation before, this is based on these previous simulation studies, when the internal wave approaches and breaks, we are going to change the current direction. Usually it starts with a depression wave, so the lower part below the wave will move basinward, but when it starts approaching the slope, the wave is going to change to an elevation wave, and in this case the zone, the water below that is in contact with the seafloor is going to move landward, and this is the moment where there will be also more turbulence and more mixing in the water that will enhance seafloor erosion and favor sediment resuspension and finally generate the nepheloid layer. Yeah, so to summarize, we are going to have very different type of deposits and processes depending on the scale at which we are looking. So if we are looking at a basin scale and large scale features like the large contour drifts, large modes, and in general large contour depositional systems, then we will be able to see rather changes in the thermohaline circulation. So we will be able to see what are the long-term changes in the bottom currents. But when we start getting a bit more into the smaller scale processes and products, so even in the seismic, sometimes we already start seeing some of them that we can identify erosional features, we can have a small scale bed forms, dunes, and even if we look at the core scale. It's probably part of this is going to be recorded in there. And here is where other smaller scale processes and also that might act at higher frequency can be very important in their formation and should be also considered. And even though they might be smaller in scale and also acting at higher frequencies, they can be preserved in the sedimentary record and they should be also taken into account. That's why, in my opinion, it's very important to know in which areas of the seafloor we can expect such an interaction so that it can be integrated in a proper way in conceptual models. Yeah, and that's everything from my side. Thank you very much.
Thank you. That was a fantastic talk. If there's any questions, feel free to, I don't know if there's a raise their hand thing here, but just unmute yourself and ask a question. We've got about five-ish minutes for questions, and then we'll move on to the next talk. You can also just type them. But while we wait for the other questions, I think one thing that was so interesting about what you showed already is just even some of those images you were showing of the Mozambique Channel, of offshore Mauritania. When you think of the range, the spatial, how quickly some of those bed forms were changing in space, I think it's pretty interesting to think about. Of course, what gets preserved in the rock record, but then as we're looking at outcrop analogs of these things, right? It's often easy to think, hey, let's keep what's happening across this outcrop to one process or to one style of bed forms. And just to think of, especially the Mozambique Channel one, I think that surprised me, just how rapid it was going from an erosional surface to dunes, to then dunes that were decreasing in sizes, and just thinking about that in the outcrop space. And then also, when you're showing that range of geomorphologies on the slope, again, understanding the long-term implications of alternative deep water systems interacting with that, but just thinking about how turbidity currents might interact with that pretty complex slope being, or slope alteration simply due to just one of these processes that you're talking about. So I think that was pretty fascinating.
Yeah, thanks. A great summary.
So I think while, and again, as all the speakers speak, keep adding your questions in the chat. We're going to have after Kevin, we're going to have a break so we can also address more questions there if necessary. Now we're going to move on to the next talk by Professor Jürgen Schieber. I think what's really exciting about the speakers that we have lined up is we're talking about a range and variety of processes. We just talked about internal waves, trying to start changing our perspective on the processes that are operating here. But then now, Jürgen's going to bring in a really interesting perspective on, we also need to change our perspective on the sediment that's actually being transported to and how it actually moves. So I think this is a fascinating series of talks today.
Anyway, so my perspective is from the other end of the scale, basically. Instead of looking at stuff that is the size of an ocean, I look at something that is the size of, a bathtub, basically. And so I'm basically going to talk about bed load transport of mud in forms of aggregates of various type. And so we got just go to the next slide here. And okay, how do I transport my slides? Okay, here we go. All right, it's a bit slow. So basically, for longest time, there has been a body of literature where people have told you what shales and mudstones are and how they should behave. The only problem when I got started on working on these things, it was already clear from my first studies that it probably isn't that way. And so my field studies basically suggested, that was 40 years ago or more, 50 years ago, that mudstones are much more interesting and dynamic in terms of depositional scenario than what's in the literature. And then later on, I got into flume studies and showed actually the underlying processes that form these the observed sedimentary features in mudstones and how mudstone beds accumulate. And so we basically took care of decades of learning opinions and put them out of their misery by doing a few good experiments. So in the beginning, of course, when I started, this was in the 80s. We looked at mudstones were not very popular really, so I didn't have a lot of turquoise to work with, and so we did a lot of outcrop studies and took very large samples and did detailed studies on those, and then we realized that instead of relatively featureless and homogeneous, we had multiple flavors of mudstones in there. They were very heterogeneous, and they obviously accumulated discontinuously, a lot of interruptions in the record. And the sedimentary structures that were preserved hinted at processes that were thought to be unapplicable to mudstone deposition. And so that basically, but on the other hand, doing detailed facies studies is something that was very doable back then, and it's very doable today. You do it right, you can get lots of insights about processes that deposited your mudstone, and the only thing you have to do is don't be afraid of what other people think. Just let the rocks talk, basically. And so this is basically one of the early studies that we did in the Catskill Delta, and that's the Sonia group. We were able to learn a lot from those mudstones simply by looking at outcrops and head specimens and thin sections. But I also learned in those early studies is that, in the early 80s, sequence stratigraphy just came on the scene, and it was usually something that you did with sandstones, not with mudstones. But looking at these mudstones that I worked on back then, you could see already that there is, this is all mudstone, bottom to top. Okay, there's not a single sand grain in here, but you can see that there's non-parallel bedding. There's packages that have different orientations. You see truncation surfaces going through, and you see that there's straddle downlap. Layers literally end at the bottom of that truncation surface. And so in sequence stratigraphy speak, of course, that would mean sea level fluctuations and lateral transport of mud. And that was sort of like, that was not in the textbooks. It was not allowed at all at that time. And so it was a bit of an upriver swim, to say the least, to get this kind of conceptual change accepted. The experimental starting point when we started experimenting with this was, let's try to understand lamination, because lamination is ubiquitous in shales. And here's this picture, is a typical laminated shales, and thin sections like this are all over the literature in the early days, and usually we interpret that, okay, sediment was slowly settling down from above, and you have multiple settling events stacked on top of each other, and that was it, end of story. But the problem is, when you start looking at these sediments, you notice that there's two kinds of lamina. There's lamina where you have, look at this thing. It's not even a millimeter thick, this lamina, and it has load structures in it, flame structures and so forth. And you see here the modern one, same thing. You have lamina that have lots of load structures in it. So that's one type of lamina. The previous one we saw was very nice flat lamina. And then you have here the lamina with irregular bottoms, and obviously stuff was settling from the top. I have no problem with that. And load structures form. So why are the load structures visible in some places and not visible in others? If this also should be physical settling, why shouldn't it look like this? So we have basically to think about what this all means. And so we have here basically, when we sort of have a scenario where physical settling is the main process, and we've replicated things like this in laboratory, in tank experiments. We saw the exact same thing happening. And then how does that contrast with these flat lamina? that is basically sort of a very fundamental divide here. Here is, on one hand, on the left side, you have gravity bringing things down to the bottom. And on the other hand, what happens here? That's the question. And the thing was that there were little hints in these laminated deposits, like little lenses of sand here, and maybe sometimes some very low angle dips of the lamina and stuff like this. So there's some slight non-parallelity of lamina, and if you have a good day, you can say, yeah, maybe it was not settling, maybe it was currents. What else do we have available to do this? And so that was a mental starting point for saying, okay, let's simply have a flume where we can push muddy suspensions through and see what happens. And that's basically this one here. So we had basically modern and ancient mudstones that contain a lot of sedimentary features. If you look at them, thin sections, polished slabs, and so forth, pretty, you see a lot. And so you see these sedimentary features, you can make deductions about depositional parameters, but you are so far out at one side of the scale spectrum that your deductions are qualitative at best. There's no experimental work to back up anything that you're seeing out there. And so it was basically obvious that we need to do experimental studies in order to get the wherewithal to make accurate interpretations of the rock record with respect to flow velocity, bed shear, and things like this. And so objectives were basically to look at mud and mud deposition under energetic conditions and see what was depositional and erosional parameters, the thresholds, the rates, and then one important thing was fluctuation. That is sort of the key of it all. And what kind of bed forms and deposition of fabrics do we get? And for this kind of stuff, flume studies are perfect because we can control the parameters like sediment concentration, salinity, flow velocity, and shear stress. And then we do get beds of mud, we get bed forms and deposition of fabrics that we can make visible by taking that flume deposit and turning it into a rock and thin sectioning and all that kind of stuff. It's a little tedious, but it's doable, and we have done it. The one thing about flume experiments with muddy suspension is, however, that the waters are murky. You basically don't see anything. It's not like a sand flume experiment where you see beautiful ripples moving along. Initially, when you do this with mud, you see nothing. You just see a brown soup, and that's it. And so we had to do a little bit, how should I say, we had to be creative to start to see. But what we found when we did those flume experiments, where we moved mud around in circles basically, and that if you have a muddy suspension, and when you having the proper flow velocities, then mud flocculates and forms bed load floccules, and those floccules can form ripples, and then those ripples can accrete to form mudstone beds. And the flow velocities for that are comparable to what you need for bed load transport of sand grains. Okay, so you could run this experiment with sand grains, and it would make ripples and form beds. You can make this experiment with mud, you get ripples, you get beds. Just one of them with much more water. And so when it compacts, of course, you barely see it. This is basically what you see initially. You see this is an example of a large Balkan ripple basically moving across a flume bottom. And this is just one of them, but you could look to the left, to the left and right. You see multiple of migrating through there. If I increase the rate of deposition, I get, instead of getting Balkans, I get more or less sort of wavy linear ripples, basically, pretty much to what the previous speaker showed in her pictures. And it's about the same scale. So we have here mud ripples that incidentally are a similar scale of sand ripples that if you had the sand. And so when I see those deep sea pictures, I'm surely tempted to ask one question. So what is the grain size of the sediment? What is it? Is it mud or is it actual sand? Because looking at the geometry and the morphology of these things, you can't really tell the difference. Anyway, so once those experiments had successfully shown that we can transport mud in bed load in the form of floccules and build up beds and so forth, and we have been able to show that this is reflected directly in the rock record, there's no question about it. We ran experiments on various other aspects of this whole story, about 20 years now. And we're trying to arrive at a physical foundation to understand mud transport and deposition. We have come some distance, but it's a lot of work because we're the only lab that is doing it actually. But we're operating from a 4-dimensional experimental matrix where we're looking at velocity, sediment concentration, salinity, and then also already mineralogy and particle type. And then we are working on the role of organic matter, which has just been published a few days ago. And then but another thing that we probably have to engage in the future is to look at sediment mixtures. How does this stuff behave? You have different kinds of clay or certain silt and clay ratios and sand involved and so forth. For example, I mean, I already said sand and mud floccules move under similar flow velocities, and we can actually have experiments where we have mud plus mineral sand grains, I mean quartz grains, and we run them at flow velocities that are above the threshold of motion for both. What we get interbedded, interlaminated sand and mud that was both deposited by the same current at the same time. Okay, and we still learn new things with each new experiment. I mean, we're having 2 flumes running with experiments right now, and we constantly run into surprises. But the surprises are not of the types that they would change the paradigm, quite the opposite, but they're telling us new aspects of the larger system, basically. So we're on a good way, but it would be nice if some other labs would jump up to the rise to the occasion, let's put it this way. It's a lot of work to be done. But anyway, we have by now proven investigative techniques of how to study muddy systems. And this is, for example, an example how we do this. We run them through experiments where we start at full suspension and then we sort of slowly step it down. And at some point, I mean, these kind of curves like this from on the part A of the diagram, that's simply sediment loss in the flume in corners and nooks and crannies and so forth. That's inevitable. You can't build a flume that has no blind spots, basically. Or if you can, it's going to be bloody expensive. But at some point, you come to a hydraulic condition where the mud really comes out, forms bedload floccules, and then the decline curves get much steeper. And this happens around here. And then you go even further, and it becomes more dramatic. The other things that you notice that salinity, you have here fresh waters, 2%, 3.5%, is not really the deciding factor of how this happens. Okay. Basically, no matter which salinity you use, once you reach a critical velocity, stuff comes out. And which is sort of, and we also played with a range of sediment concentrations. And basically, sediment concentration that you can imagine in nature to happen in tidal channels or in river channels and so forth would perfectly behave themselves like this. So the important thing is mud gets deposited because of the floccule formation at much higher velocities than the literature gives it credit for usually. And so then, you can see that here's just the flow velocities, and you see that for this particular case, at about 25 centimeters, it gets coarser no matter what you do. There's a sort of a sharp dividing line here. And you can do floccule counting and show it graphically as size plots, so that the floccules get larger as bed shear drops, become more stable, and the critical velocity is indifferent to a wide range of salinities and suspended sediment concentrations, but is still dependent on minerals, okay? Different minerals have different thresholds, basically. So we have results that pretty much have stood the test of time. And for mud, basically, arriving at the bottom by gravity settling is the easy part. They all do that, no matter where you are. Gravity is your friend. But the fact of the matter is also that at most ocean basins, the water is not stagnant. It moves. Currents are common, and currents can and will move mud. Anything that arrives at the top of a bottom current will get mixed in with it and then move along with it, and it will flocculate and it will make little ripples. So these bottom currents are strong enough to move mud in suspension, for sure. And when flow velocity falls below the critical velocity of sedimentation or the shear stresses associated with that, you get sand-sized floccules that move in bed load, they form ripples and build up muddy strata. And the cool thing about it is that this is basically water depth independent, okay? And the things that we show in most of our experiments as sort of centimeter scale ripples, maybe spaced 10, 15 centimeters apart or something like this. And those are basically the workhorses of transport, of mud transport, when there's currents with suspended material moving on. They always will make these ripples, but then the ripples can become part of larger bed forms. You get mega ripples. We have fossil examples of that. And I would venture that even larger muddy bed forms in the deep sea are basically built ultimately by these centimeter scale ripples that migrate up one side and then deposit the sediment on the other. As I said already, these processes are largely insensitive to sediment concentration and salinity and reflect mostly mineral properties, and they're also prone to biological modification. In our experiments, when the experiment runs too long, even if we start with a clean flume and mineral dust and stuff like this, after some time, there's biofilms forming, and they change the behavior of things immeasurably within a week or something like this. And so out in the open ocean and so forth, where there's no shortage of organic matter, the pure mineral behavior that we are trying to capture in flumes is modified by biological processes, but it's all good because it usually tends to increase or raise the thresholds for the critical velocity and stuff like this. So actually, it makes the mud deposit easier up to a point. Everything is like that. So everything flocculates once it's small enough. And we can do experiments like this with quartz sand. We will flocculate when it's fine enough. And mudstones can be composed of floccules. Wait a moment, sorry. We can have, so we have floccules is one way mud aggregates. Then we also have, if there's a muddy substrate, it can be ripped up by currents, and little bits and pieces of that millimeter size will be transported. They're slightly denser than floccules, but not much. They behave pretty much the same. And then we also have mudstone lisics, or in most mudstones, combinations thereof. And so deciding which one you are looking at, what type of mud aggregate, you have to use high-end petrography, but it's technically a simple matter. Your understanding starts at the petrographic level when you understand what kind of aggregates you used to have when this stuff was deposited. And the process that I described, you know, the aggregation into floccules and transport of bed load mud and stuff like this, works in a roadside ditch just as well as in deep sea, and it's easy to watch. Ultimately, whatever you do with the mud, the final current wins. This is just an example of, this is a roadside ditch after a bit of a rain. And so you can see the muddy suspension moving through here. You can see here small bed forms forming into channel here. Okay, this stuff is very watery. It's 80% plus water basically. It's liquid more or less. You try to touch it. And here this forms nice ripples. Okay, rippled stuff, bang. And it's all mud. Okay, and this is basically a roadside ditch, and I don't imagine that the rules change, but just because you have a kilometer of water on top of it. So a lot of this, the deep sea drifts, contourites, when they're quite muddy, which sort of some of them are, it's probably this is a process that I just described that actually allows the mud to move and to get deposited in nicely layered deposits. And just to show you what the mud aggregates look like, here this would be the floccules that we produce, for example, in flumes, and which also have been observed in natural deposits, in natural settings. Then we have, for example, fecal pellets is another category of mud aggregates, and they travel together, they form sand-sized particles, and they're fine-grained, and they get compacted and flattened over time. This one is lots of coccoliths, basically. And then you have here, this is a more generic ancient deposit, lots of different kinds of muddy, flattened aggregates in there. These are probably wrap-ups from the master substrate somewhere else. And then finally, you have mudstone liths like this one here, which are also part of many mudstones, because just because mud weathers on outcrop doesn't mean it completely breaks down. Oftentimes, a certain part of the outcrop travels as sand-sized and silt-sized fragments of that mudstone instead of as individual mineral grains that you see here. And the consequences of this is, of course, this here, for example, I got this sample from the Adriatic, and I was told it's a mudstone, a mud. Sorry, there was lots of water in it. This is a mud that I was sent, 200 microns here. But when you prepare it properly so that you can see the individual particles, and it's not easy. I mean, this is 80% water when it was collected, okay? So, but we have our ways to do this, and you can see there's definitely not mud particles, mud-sized particles, and see here that actually you have rounded fragments here that are basically the mudstones that came out of a river not too far away. Mudstone, the river basically spit out suspended material, but it also spits out a whole bunch of fragmented, transported mudstone liths, basically. And so you take one of the Schlumberger tools to tell you what kind of rock you have when you drill it. It would, of course, return this as a mudstone, but hydraulically, you're looking at a sandstone. And so that will tend to throw you off quite a bit if you don't look at the rock itself. So you have to trust your eyes, because that's where the insight really starts. This is just to give you an idea. This is in the flume experiment, and you can see that we have a clay bed that has markers in it, and we have a slight clinoforms forming, basically. And then you see when you break these layers apart, you see ribbon forostructure in it, and you know that every one of these layers has been accreted and deposited by migrating ripples, and not by stuff falling out of the water column. And you find these same textures in the rock record. It's just to give you an idea of how this works. We have an experiment here that ran for about a week, actually several weeks, but this is the first week of it. And we simply filmed from this transmitted light how the ripples are moving by, And every time a ripple moves by, it leaves a little bit of itself behind, and gradually the bed builds up. And it basically consists of the tail ends of many, many ripples that have migrated through over time, and the final deposit is thinly laminated, but it was deposited by ripples. And that's a pretty universal theme that we have seen in many rocks, all the way from Archean to modern. Okay. So the physical process of flocculating mud and then having transportable floccules building ripples and beds and stuff like this, that has been going on, because physics didn't change, hopefully, over the last 4 billion years for a long time. And there, just, normally when people think of mudstone, they think about clay and stuff like this, but I didn't mention the minerals. We do, of course, experiments with clay, lots of them, but it works. And I also mentioned, however, that it also works with however fine the stuff is. Fine stuff here, like coccolith, for example, less than 10 microns usually. This is pure coccolith sediment, basically. It flocculates. It forms quite nice large floccules, and it builds up beds. So a coccolithic limestone that's laminated, in my opinion, was probably also deposited by migrating ripples that consisted of flocculated coccolith. In the laboratory, in the flume, this is how it works. Exactly the same. Different mineral, but the rules are the same. We're planning to do experiments with all other sorts of other crazy things, like maybe feldspar dust or olivine dust or something like this. And I guarantee you it will still behave the same. So this is just, I showed the coccolith experiment. And this is literally just came out of the lab a few days ago. And we have here fresh water, 2%, 3%, 3.5% salinity. And you notice that the systemic decline curves get steeper at about 25 centimeters per second, which is the same what we see for clays and silts and stuff like this. So basically, the bed load floccules form at critical velocities of sedimentation that are common to other fine-grained materials. And I expect, and I've already shown this before, this happens regardless of mineralogy. It's just when things get small enough, they want to flocculate. And here, this is a picture actually from an outcrop in Romania, the bituminous malformation. And this is basically cross-bedded mudstone. Okay, this is a mega ripple that is the next bed form up from the ripples, basically. And we have pictures that a student of mine gave to me from ODP 401. And here you see also it's a mudstone, and you see inclined bedding here. It's sort of quite similar to the stuff that you see in outcrop in Romania. And we have other examples of these kind of cross-bedded intervals in mudstones elsewhere. So in summary, muds and clays are prone to form large floccules over a wide range of conditions. Aggregates that travel in bed load form ripples and higher order bed forms and build up muddy strata. The pelagic settling of mud components is commonplace, but pelagic input is invariably reworked and reshaped by bottom currents. The coarse sand and silt that is interlaminated with mud layers does not automatically imply a change of flow velocity, because these things can be deposited at the same time under the same shear stress regime. The erosion of seafloor muds produces soft clasts that can be transported by bottom currents and then accumulate to form new mud beds. And in many respects, looks very much the same as the ones primary deposits. Mudstone lithics, anywhere from millimeter to micron size, are a common component of marine muds in both shallow and deep settings, and they also imply bottom current activity. So this is sort of there's a short version of what we have been doing over the last 20 years, and we're still finding new things, but fundamentally, there's no reason to believe that mudstones need low energy conditions to get deposited. They actually seem to deposit just fine when energy conditions are much higher than what normally they're told they need to deposit. We have shown it so many times in flume experiment, there's no question about it. And so I don't know if I've exhausted my 15 minutes or not, but this whole topic, I could talk about for hours and show you all sorts of beautiful pictures of it that makes a point, but maybe some other time. But it's in 15 minutes is about all I can do. I primarily wanted to point out that there is a process that is natural, happens all the time, wherever you go, when there's suspended mud. And that is a process that probably deposited most of the mud that you see in the rock record. Okay, thank you.
Excellent. Thank you, Professor Schieber. Yeah, no, that was a fantastic talk. I think for the sake of time, we're going to jump to Kevin Bohacs now. After Kevin, we're going to take a break where we can also address more questions. Again, I completely forgot, there's a whole separate questions tab where you can record your question, your name. So please put your questions in there. I'm looking at that now. I apologize for not looking at it before. And the speakers can all keep addressing those questions as we continue on. So it's a great place to post your question. But again, thanks for a great presentation there, Professor Schieber. And Kevin, go ahead.
Unmuted. That's a good thing. Okay, great. Thank you so much. What a great day. Good day to everyone. I'm here to speak on behalf of benthic current dominated depositional systems, also called contourite depositional systems, and to give an integrated picture of this end member, especially at the log, outcrop, and core scale. I will also point out the key influences on mixed systems and some specific recognition criteria. First, we'll say a very few words about deep water benthic currents, their wide variety and widespread distribution and effects on sediments, as we've heard. The bottom line of this part is that such currents are everywhere, and what would be weird is if such currents were absent. And Professor Schieber just showed us a bunch of the evidence in the rock record. Next, we'll discuss the depositional systems associated with those benthic currents, their characteristics and recognition criteria, as well as their relation to mixed systems, with the bottom line here that they are variable but distinctly different from deep water fans. Benthic currents are one of three main modes of sediment delivery to deep water systems, the others being sediment gravity flows and direct settling from suspension. The information in this talk comes from both the modern and the ancient. In the modern oceans, we have extensive current measurements as well as observations of more than 260 sediment bodies associated with benthic currents, shown in tan and numbered on this map. In the ancient, we have more than 42 examples from 26 basins across all continents of Permian to Pleistocene ages so far. Now, there has been a fair bit of work on the oceanographic processes associated with contourite depositional systems, as Dr. Garcia presented earlier. However, as to the products of those processes, especially vertical and lateral successions in the rock record at the well log and core scale, not so much. Despite some good work on their appearance in 2D views of the seafloor and multi-channel seismic data, proposed facies models and outcrop examples are still warmly debated, and that's kind of why we're here today. And I look forward to hearing especially what Professor Hernandez Molina has to say in the second half. What's new in this talk is a proposed set of integrated recognition criteria from seismic through well log to core, outcrop, and thin section. Here's where that integrated approach leads. These systems are the result of frequently repeated episodes lasting hours to months of high speed but subcritical traction currents flowing along slope. They contain a wide variety of sedimentary features. They are distinctly different from deep water fan systems, which are dominated by downslope, frequently supercritical sediment gravity flows. Of course, Mother Nature doesn't always cooperate with our neat categories, but in general, we can consider contorite depositional systems and deepwater fans as end members of a spectrum of mixed deepwater systems, marked by various degrees and timings of interactions of along slope and downslope currents. Contorite depositional systems are themselves variable to some degree, but distinct from those systems formed by episodic downslope flow. Those distinct differences arise from the characteristics of deepwater benthic currents, which we will now discuss for a moment. The floor of the ocean beyond the continental shelf is affected by many types of currents. These currents include thermohaline-induced geostrophic benthic currents, of which contour currents are only one type, denser water eddies, internal waves and tides, solitons, benthic storms, and tsunami-induced currents. All these current types share the fact that they are driven by gravity working on water masses of different densities due mostly to temperature and salinity. The ubiquity and variety of benthic currents was well summarized by Walter Munk back in the 1980s, one of the grandparents of physical oceanography, who said, "No one has ever reported an interior calm in the ocean." Deepwater benthic currents are present throughout the world ocean, as shown in shades of blue on this compilation by Thran et al. The most energetic bottom currents occur mainly in three settings: along the western boundaries of ocean basins, near sites of deepwater formation, mostly at high latitudes and from the Mediterranean, and in areas that are tightly constricted by topography. So with that very short introduction to the key processes, let us now discuss their products. Benthic currents redistribute mud and sand that is delivered downslope by sediment gravity flows, mostly. Benthic currents form a wide variety of erosional and depositional sedimentary features and bed forms at the mesoscale, as well summarized by Robesco and Stowe and that crowd. And we'll hear more about this from the other panelists. At the macro scale, benthic current depositional systems construct substantial sedimentary bodies that are elongated generally parallel to the continental slope. These systems are widespread, with more than 260 separate sedimentary bodies identified, shown here in tan, and they cover about 13% of the seafloor. They are most common off east coasts, formed under the influence of western boundary undercurrents. Seismic to core scale integrated analysis reveals that contorite depositional systems comprise two main geomorphic elements with distinct facies: a contorite drift, which is the main sedimentary body, and a contorite channel or moat, typically found slopeward of the drift. These two main geomorphic elements each have characteristic seismic, well log, and physical and biogenic attributes. The two main elements also have characteristic lateral and vertical stratal stacking patterns, as summarized here. We will discuss each in turn. A contorite drift is the larger volume, typically finer grained part of a contorite depositional system that occurs basinward of its associated contorite channel. The map view example is from the North Atlantic, and the profile example is from the Caspian Sea, which is a lake, by the way, so you don't need salt to make a contorite system. Kind of following up with what Jürgen showed us about the effect of salinity on flocculation. Drifts range in shape from thin tabular sheets, discontinuous to continuous, to mounds at the multi-kilometer scale. These morphologies are also expressed at the tens of meters scale, shown here in outcrop in onshore Angola. Tabular at the base, mounded in the middle, and overlain, in this case, across a nonconformity by a fan channel. In core, we see that no sedimentary structures are unique to this setting. It shares many attributes with sediment gravity deepwater systems. However, contorite depositional systems are dominated by evidence of persistent and frequently recurrent traction transport, cross-bedding, small and larger scale, scours, and lags. And these are the key recognition criteria, along with common to abundant deepwater euryhaline body fossils. As with all other depositional environments, it's essential to place one's detailed observations into their overall stratigraphic and geomorphic paleogeographic context for the most robust interpretation. So in detail, the drift can be divided into 3 subfacies based on their proximity to the contorite channel. Distal drift facies accumulate farthest from the contorite channel. They are typically fine-grained argillaceous siliceous with very sparse glauconite. It is mostly bioturbated with sparse discrete deposit feeding and dwelling traces. This facies has an overall mottled appearance. Much of the original bedding is recorded only as diffuse bands of different colors with indistinct contrast. Ooh, isn't that interesting? Where'd my pictures go? Oh well, feature. Preserved sedimentary structures include sharp-based fossil lags, as well as the very sparse millimeter scale planar and graded beds. Biogenic content is mostly planktonic microfossils, along with some transported fragments of shallow water forms and fragments of deep water thin-walled bivalves. Closer to the contorite channel, the medial drift facies is characterized by mixed grain sizes and lithologies, as well as faster sediment accumulation. This facies comprises calcareous sandy mudstone and siliceous argillaceous muddy sandstone with a few brown glauconite grains and organic matter-rich argillaceous pellets. Primary sedimentary structures and discrete trace fossils are more commonly preserved than in the distal drift. Traces are mostly deposit feeding and dwelling with some locomotion traces. Sedimentary structures include scours, lags of coarser grains and fossil fragments, current ripples, starved current ripples, and millimeter scale planar and graded beds. Fossil assemblages are similar to those in the distal drift deposits. The proximal drift facies accumulates yet more quickly in the area of a drift that is closest to the contorite channel. This facies comprises various compositions and a wide variety of grain sizes: argillaceous, calcareous, siliceous, and bioclastic mudstone, sandy mudstone, muddy sandstone, and sandstone. Glauconite pellets can constitute as much as 10% of the sand size fraction. Decimeter scale bigradational or contorite sequences are characteristic of this facies. More about these in a moment. Burrows include discrete deposit feeding, dwelling, and locomotion traces. The mudstones are burrowed, but the sandstones preserve many primary structures, including scours, starved current ripples, lenticular and flosser bedding, planar and wavy bedding, and muddy rip-up clasts. Fossil assemblages are similar to those in the medial drift facies, with the addition of fragments of larger benthic organisms such as crustaceans and echinoderms. When we rack up all these criteria, we see that they are differences that make a difference. Now, I'm sure you're thinking that's all very fine, but where are the contorites? But strictly speaking, contorites are these cute little decimeter scale stratal successions that gradationally coarsen, then fine upward, also known as bigradational sequences. Contorites have been viewed as conceptually analogous to the Baumas turbidite sequence. Contorites superficially resemble hyperpycnites in their bigradational grain size profile, but differ from them in the character of bed context, type and abundance of preserved primary sedimentary structures, content of land plant debris, and trace fossil types, abundance, and diversity. The reason I have not stressed contorites is because contorite sequences are not found throughout all contorite depositional systems. It turns out they are most common in the proximal drift facies and not common in nor characteristic of coarser grain contorite depositional systems. Now onto the other geomorphic element, contorite channels and their fill. These channels are elongate erosional depressions on the slopeward margin of a contorite drift. They can be relatively straight and oriented along slope, or sinuous and oriented oblique to the slope. They are characterized by the presence of truncated reflection seismic reflections at their base. Within these channels, sediment moves under the influence of unsteady benthic currents and overflows onto the adjacent contorite drift. As with the drift facies, channel fills have pervasive evidence of traction transport under episodic but frequently recurrent higher energy episodes. In contrast with the drift facies, however, these strata thin and fine upward over the multi-meter scale, and bioturbation increases upward with significant burrowing only in the uppermost channel fill. The channel fill facies is characterized by scours, rip-ups, lags, unidirectional crossbeds that thin upward is shown in D and G, flosser beds and mud drapes in A, B, and C, wavy bedding in H, sigmoidal crossbedding and reactivation surfaces in D, I, and J, mudstone rip-up class in E and F, along with macrofossil fragments of benthic and planktonic shelfal and abyssal taxa, and low diversity burrows, mostly deposit feeders, and bioturbation increases upward. When we put all these subfacies together, we see that they are indeed distinctly different and stack in a recurrent pattern. A complete succession comprises a relatively thick lower interval that coursens upward, overlain by a thinner interval that finds upward, all at the scale of many meters, and not at the decimeter scale of a wee contorite bedset. The lower coarsening upward interval records accumulation in the drift part of a system. Across a sharp, generally erosional surface, the upper fining upward interval records accumulation in the associated channel. And these subfaces show up rather clearly on well logs, at least on total and spectral gamma logs. Conceptually, this is how the vertical succession records the oblique lateral migration of the contorite drift and associated channel, from the initial accumulation of a distal drift through the medial and proximal drift to the channel fill facies. So this vertical succession represents the fundamental depositional motif, the building block at the parasequence scale. Their thicknesses in this case range from 1.8 to 7 meters and average about 3 meters. And they can be correlated for many tens of meters along slope and tens of kilometers cross slope. These building blocks stack in systematic patterns, typically progradational to aggradational, as shown on this well log, to record the long-term accumulation of a benthic current-dominated depositional system. So there you have it, the N-member contorite depositional system, and we'll hear more about recognition criteria from panelists in the second half. We can now consider how to differentiate them from the other deep water depositional systems, starting at the other end of the spectrum, deep water fans. In general, contorite depositional systems are characterized by subcritical traction transport in relatively clear water under frequently recurring persistent currents that flow mostly along slope. In contrast, N-member deep water fans are dominated by sediment gravity transport under episodic short-lived supercritical currents that flow mostly downslope. For recognition in the straddle record, contorite systems are characterized by pervasive bioturbation and an asymmetric cross-section with straddle continuity oriented mostly along slope and basinward. Seismic reflection patterns are relatively uniform and thin gradually by downlap, and their spatial extent is generally greater than many deep water fans. Of course, contorite systems represent one end member of a spectrum of deep water systems that record various degrees and timing of interactions of along slope and downslope currents. And I look forward to hearing much more on how to recognize where one is on the spectrum throughout this session. What does occur to me, however, is that the essential differences among these systems relate to both the relative abundance of along slope clear water traction transport versus downslope sediment gravity flow sedimentary features, and to their 3D distribution. Now, there are reasonably robust recognition criteria at the system scale: the geometry and distribution of levees and lobes, the geometry of the drifts, the migration direction of channel scours and fills, and the geometry and relative size of associated channels. Now, how these translate down to the well log, core, and thin section scale is what we need more work on. So, in conclusion, you will be happy to hear, The essential attribute for the recognition of contorite depositional system facies is the pervasive influence of persistent along slope benthic currents and subcritical traction transport in a deep water setting. As for mixed systems, well, most I can tell you is what would be weird is not seeing the influence of benthic currents in deep water settings. And we will hear more about mixed systems from Drs. Rodriguez and Serrier after the break. That was a lot to cover in a short time. Let me bottom line it for you. Contorites do not tell you everything you need to know about contorite depositional systems, just as turbidites do not tell you everything you need to know about deep water fans. Or rather, contorites are to contorite depositional systems as turbidites are to deep water fans. Potentially common in some parts, but not the whole story. If you happen to have missed any of that, we have written most of it down in SCBM's Handbook of Siliciclastic Facies in chapters 8 and 9, and in AAPG Memoir 126. We thank our colleagues and collaborators for sharing their insights with us, all the authors of the most excellent publications from which we drew our examples, Drs. Emma, Fabian, Lillian, and Stan for organizing this meeting, and you for your very kind attention. I look forward to your questions and a very lively session. Thank you. And now a word from our sponsors. So coming up in 11 days, the Gulf Coast section of SCPM will be hosting a 3-day conference in Houston in memory of Peter Vail, Bob Weimer, and Larry Sloss, sort of talking about where sequence stratigraphy and how we got to where we are. It's a chance to hear the old guys talk one last time so you can hear a little bit about how the sausage was made. And we encourage you to join us. Thanks.
Thanks, Kevin. That was a fantastic talk. We do have some time for questions. Let's do maybe 5 minutes of questions before jumping into the break. And we'll do a break of about 5 minutes. And I know we have some polls coming up, so please come back and then we'll get back into more talks. There's some questions that got posted here. I'm going to read one out unless anybody wants to unmute themselves and read it. One was here from Tim Demko. Shouldn't we have different facies models for moats, in parentheses, long linear hydraulic jumps versus channels, dominantly uni or bidirectional flow, because they may have similar geometries and maybe even geomorphologies, but different products?
I think that's exactly right. The products, because the reason I emphasize channels is moats are, as I've seen them, are pretty much an erosional feature, and sort of in the way I was talking about them. Essentially, once they start to become depositional, once the sediment starts to accumulate in them, they're effectively a channel. So that's definitely an open question: is how those scour lens shaped cross section features fill in, whether it's from one end with the traction transport going across there, or is it some other processes, some of the supercritical sediment gravity flows and whatever else. So definitely an open question.
Okay, yeah, no, that's excellent. There's another talk from Morgan Sullivan. I guess he's asking why a contorite channel and not a turbidite channel. The fill looks like a classic turbidite channel, and seismically might be expressed that way too. I guess, do you have any thoughts on, some of the differences internally and maybe geometric apart from orientation between turbidite channels and these contorite channels?
Right. So if we can see the rocks, what we'd see in the contorite or the benthic current dominated ones are traction transport. We won't be seeing all the supercritical turbidites, et cetera. Whereas, in terms of from the seismic scale, that's going to be a lot more challenging, and that's going to require the larger scale regional context, I think. The other thing is a lot of things we think of as classic turbidite channels probably have a fair bit of benthic currents, moving stuff around. So I would actually posit that we've seen very few pure turbidite channels. That there's always going to be some water flowing around and rearranging things. And it's going to be, it's a spectrum, and we're humans. We like to split stuff up. We like to put end members, but you know, in nature, Mother Nature doesn't know what we're thinking, so she's going to do what she wants to do.
No, that's interesting. And I think just the points you were making too about the changes across in facies across the drift. I know you did point it out, you know, as simple as, you know, a net to gross difference across that drift. But just thinking of, as you were going through it, you know, how much can we confuse that geophysically with something that might look a lot more sandy or might have more of an impedance contrast than we think over a broad scale. Just interesting to kind of place that in context when we're thinking of acting on some of these models, and you know, and defining some of these as reservoir potential or trap potential. There's one more question that popped up, and then we'll answer this and then jump to a break. From Breno Goldenberg, how can we distinguish the point at which a reworked turbidite should be considered a contourite?
I would say, unless you see the classic, you know, Bauma sequence, if you will, or the typical supercritical flow bed forms, once it starts to flip over into anything that's larger scale than a ripple, that means you had persistent unidirectional currents going for more than a few minutes. You're talking about hours to get dunes organized, right? That's my flume experience in the old days. So yeah, so I think once you start to see things that are the decimeter scale cross bedding, and you know, a lot of those we see the mud drapes and the bundles. So you're seeing evidence in these deep water deposits of the tidal modulation of the benthic currents that our first speaker was talking about. So
Excellent. All right. Well, again, thank you for addressing those questions, and a really good talk. Right now, we're going to go on a break. Let's keep it to around 5 minutes and return around 10:36 or 36 past the hour, wherever you are. When you do come back, take a quick look on the screen, because we are showing some other events happening in the world of deep water sedimentology and stratigraphy. We will also send those out as well. Please go look at those, because there's a lot happening. And also, when you come back, we're going to launch a poll on the specific questions associated with this forum and for SEPM. So please take the time to listen to those. Yeah, thank you. We'll return at 36 past the hour.